There is a machine sitting in a clean room right now, wrapped in layers of protective foil, surrounded by engineers in white suits, and it is about to do something that no instrument in the history of human civilization has ever done. It is going to look at 1 billion galaxies at once. It is going to map the invisible architecture of the universe. It is going to answer questions that have haunted physicists and astronomers for decades. Questions about what the universe is made of, why it is expanding faster than it should be, whether there are other planets like Earth in our galaxy, and whether we are truly alone among the stars. And it is going to do all of this 8 months ahead of schedule. NASA's Nancy Grace Roman Space Telescope is ready to fly. On April 21st, 2026, NASA Administrator Jared Isaacman stood at the agency's Goddard Space Flight Center in Greenbelt, Maryland, and announced something that almost never happens in the world of major government science projects. A mission of this scale, this ambition, and this technological complexity had come in under budget and ahead of schedule. The original launch commitment was no later than May 2027. The Roman team is now targeting as early as September 2026, 8 full months early. And the implications of what this telescope is about to show humanity are almost impossible to overstate. To understand why Roman matters so much, you first need to understand what we do not know. Right now, in the year 2026, after centuries of scientific progress and decades of space-based astronomy, human beings have mapped and cataloged less than 5% of everything that exists in the universe. The other 95% is invisible to us. We cannot see it. We cannot touch it. We can only measure the gravitational effects it has on the things we can observe. Scientists call it dark matter and dark energy. And together, these two invisible forces and invisible substances make up the overwhelming majority of all the matter and energy in existence. Everything you have ever seen, every planet, every star, every galaxy, every atom in your body, all of that combined represents roughly 5% of what is out there. The rest is mystery. Roman was built to begin solving that mystery at a scale that no telescope before it has ever attempted. The story of how this telescope came to exist is almost as dramatic as the science it is about to do. The mission was first recommended back in 2010 by a National Research Council committee that reviewed the priorities for the next decade of American astronomy. It was named the Wide Field Infrared Survey Telescope at the time, and it was flagged as the single highest priority for the coming decade. But priority on a list does not mean money in a budget. For years, the project fought for funding. It survived multiple attempts at cancellation. It navigated the chaos of changing presidential administrations and dramatically shifting budget priorities at NASA. In 2025, the Trump administration proposed cutting NASA's science budget nearly in half, from $7.5 billion to $3.9 billion. And Roman was explicitly listed as a mission to be canceled. Congress rejected that proposal. Roman survived. And then, while its political enemies were sharpening their knives for another budget fight in 2026, the telescope quietly finished construction, passed its tests, and announced it was ready to launch before those knives ever reached it. In 2020, NASA renamed the mission the Nancy Grace Roman Space Telescope in honor of the agency's first chief of astronomy. Nancy Grace Roman was a pioneering scientist who spent her career fighting for the recognition of women in science while simultaneously building the institutional foundations that made space-based astronomy possible. She sat on committees and argued in budget meetings and pushed NASA toward the vision of telescopes that could observe the universe from above the distorting blur of Earth's atmosphere. Without her work in the 1960s and 1970s, the Hubble Space Telescope might never have existed. She died in 2018, and she did not live to see the observatory that bears her name reach completion. But she would have recognized exactly what it was built to do because she spent her entire career trying to make it possible. The telescope finished construction on November 25th, 2025, when engineers at Goddard Space Flight Center completed the final integration of its two major segments in the largest clean room in the facility. NASA Associate Administrator Amit Kshatriya stood before the assembled team and said the moment represented a defining milestone for the agency. Senior project scientist Julie McHenry put the capabilities of the finished telescope into language that anyone could understand. She said that 1 month of observations from the Roman Space Telescope would be equivalent to a century of data from the Hubble Space Telescope. Read that again. 1 month of Roman equals 100 years of Hubble. That comparison sounds impossible until you understand the engineering behind it. The Roman telescope has a primary mirror that is 2.4 meters in diameter, essentially the same aperture as Hubble's, but the similarities end there. Roman carries a 300 megapixel infrared camera called the Wide Field Instrument, and that camera has a field of view that is at least 100 times larger than Hubble's imaging cameras. And when Hubble takes a picture, it sees a tiny patch of sky, a pinhole of the cosmos. When Roman takes a picture, it sees an enormous swath of space at the same sharpness and resolution that Hubble achieves in that tiny patch. NASA Administrator Isaacman described it at the April press conference as surveying capabilities over 1,000 times faster than Hubble, with the ability to chart 200 times. More sky in a single image. The team at Sky and Telescope reported one engineer saying that the images Roman captures will be so large there is not a screen in existence large enough to display them at full resolution. Roman will orbit the Sun at a special location called the Sun-Earth L2 Lagrange point, approximately 1 million miles from Earth in the direction directly away from the Sun. This is the same orbital location where the James Webb Space Telescope operates. At L2, the telescope is shielded from direct sunlight, can maintain a stable temperature, and has an unobstructed view of deep space. From that position, Roman will carry out 3 core surveys during its 5-year primary mission that will together account for approximately 75% of its observing time. The first survey is the High Latitude Wide Area Survey. This is Roman's deepest and most ambitious project. It will combine infrared imaging with spectroscopy, the technique of splitting light into its component wavelengths to identify chemical signatures, to map more than 1 billion galaxies spread across the universe. These galaxies span enormous stretches of cosmic time, some of them as they existed when the universe was only a few billion years old. By measuring how those galaxies are distributed and how they cluster together, scientists will be able to trace the large-scale structure of the universe across time. And hidden in that structure, like fingerprints on a window, are the signatures of dark matter and dark energy. The way galaxies cluster together is shaped by dark matter's gravity. The rate at which that clustering has changed over billions of years is shaped by dark energy's repulsive force. Roman will produce a 3-dimensional map of the universe stretching back more than 11 billion years, the most detailed cosmic map ever constructed. The second survey is the High Latitude Time Domain Survey. Instead of scanning new territory, this survey will return to the same region of sky again and again over months and years, looking for things that change. The universe is not static. Stars explode. Black holes flare. Galaxies shift and evolve. By observing the same patch of deep sky repeatedly at high precision, Roman will detect tens of thousands of type Ia supernovae, a specific class of stellar explosion that scientists use as what astronomers call standard candles, meaning objects of known brightness, because these supernovae always explode with a predictable luminosity. Measuring how bright they appear from Earth tells scientists exactly how far away they are. String thousands of these distance measurements together across cosmic time, and you can reconstruct the precise expansion history of the universe. That history is one of the most important tools scientists have for understanding dark energy and testing the theories that attempt to explain it. Dark energy is perhaps the most profound mystery in all of modern science. In 1998, 2 independent teams of astronomers studying distant type Ia supernovae discovered something that upended everything cosmologists thought they knew. The universe was not just expanding, it was accelerating. Something was pushing galaxies apart at an increasing rate, working against gravity across the largest scales in existence. That something was given the name dark energy. But naming something is not the same as understanding it. In the decades since that discovery, physicists have proposed dozens of competing theories about what dark energy actually is. Some think it is a property of space itself, a constant energy density built into the fabric of the universe. Others think it is a dynamic field that changes over time. Others think it is evidence that Einstein's equations of general relativity break down at cosmic scales and need to be replaced with something new. Roman's data will be the most powerful test ever applied to these competing theories. And whatever the data shows, it will change how humanity understands the nature of reality at its largest scale. The third survey is the Galactic Bulge Time Domain Survey. This one points the telescope inward toward the dense star fields at the center of our own Milky Way galaxy, and it is hunting for planets. The technique Roman will use is called gravitational microlensing. When a star passes in front of a more distant background star as seen from Earth, the gravity of the foreground star bends and magnifies the light from the star behind it, creating a brief brightening event. If the foreground star has planets, those planets add their own tiny gravitational signatures to the brightening curve, and scientists can detect them even if the planets are far too small and too faint to be seen directly. Roman will monitor the galactic bulge continuously, capturing changes in star brightness every few minutes across millions of stars simultaneously. The mission is expected to detect more than 100,000 distant exoplanets using this method. And crucially, microlensing is uniquely good at finding planets in the outer regions of solar systems and free-floating rogue planets that wander through the galaxy without a parent star. These are worlds that no other telescope technique can reliably detect. Roman will reveal an entirely new population of planets that we currently have almost no data on. But Roman is not finished yet. It carries a second instrument that is unlike anything that has been flown on a major space observatory before. The Coronagraph instrument, designed and built by NASA's Jet Propulsion Laboratory in Pasadena, is a revolutionary piece of technology that blocks out the blinding glare of a star with extraordinary precision, allowing scientists to photograph the much fainter planets orbiting that star directly. Coronagraphs exist on other telescopes, but the Roman coronagraph will suppress starlight to contrast levels far beyond anything previously achieved in space. JPL coronagraph scientist Vanessa Bailey said it will be more stable than any previous instrument, enabling unprecedented suppression of starlight. This means that, for the first time, scientists will be able to take direct images of mature, giant planets orbiting nearby stars in their visible light. Planets that are older, colder, and in closer orbits than the superheated young worlds that earlier direct imaging techniques have managed to capture. The Roman coronagraph is officially a technology demonstration, meaning its primary role is to prove what is possible for future missions. But the science it returns along the way could include the first direct photographs of worlds that look more like the planets in our own solar system than anything we have seen before. After Roman's 5-year primary mission is complete, the data it will have generated is almost incomprehensible in volume. NASA has already built a cloud-based platform called the Roman Research Nexus specifically to handle the flood of incoming information. The mission is expected to produce approximately 20,000 terabytes of data over its lifetime. By comparison, the entire Library of Congress in digital form represents only a fraction of that volume. Astronomers and researchers around the world will spend years, perhaps decades, mining Roman's observations for discoveries. The survey data will be made publicly available, meaning that scientists at universities and observatories in every country on Earth will have access to the same cosmic maps that American researchers do. Some of the most important discoveries that Roman enables may not even be made until years after the mission ends, when artificial intelligence systems powerful enough to sift through billions of galaxy measurements have been applied to the full dataset. The telescope will travel to Kennedy Space Center in Florida in summer 2026, where it will undergo final preparations at the Payload Hazardous Servicing Facility, the same building that has processed dozens of major spacecraft for launch over the past 4 decades. Kennedy Space Center has been actively upgrading that facility in anticipation of Roman's arrival, including installing new HVAC systems, upgraded air showers, and improved clean room infrastructure. After fueling and encapsulation, Roman will be placed atop a SpaceX Falcon Heavy rocket and launched from Launch Complex 39A, the same pad that once sent Apollo astronauts to the moon, targeting early September 2026. The fact that Roman has reached this point at all, given everything that tried to stop it, is a story worth pausing to appreciate. This project survived the cancellation lists of 2 separate presidential administrations. It survived years of budget fights in Congress. It survived the pandemic. It survived the government shutdown of 2025, during which NASA's Goddard Space Flight Center began consolidating facilities and closing buildings, yet continued Roman work as an expected operation. It survived every bureaucratic and political obstacle that the American government system could throw at a science mission, and it came out the other side 8 months early and under budget. NASA Administrator Isaacman called it a true success story of what becomes possible when public investment, institutional expertise, and private enterprise come together on a mission that matters. What makes Roman's timing so significant is the moment it arrives in human scientific history. The James Webb Space Telescope, launched in December 2021, has already transformed our understanding of the early universe. Its deep infrared observations have revealed galaxies forming just a few 100 million years after the Big Bang, earlier than most models predicted. It has found complex organic molecules in the atmospheres of distant exoplanets. It has mapped star-forming regions in stunning detail and peered through cosmic dust clouds that were opaque to Hubble. But Webb is a deep-field telescope. It looks at small patches of sky with extraordinary sensitivity. Roman's strength is the opposite. It looks at enormous areas of sky with the same sharpness that Webb brings to tiny patches. These 2 observatories are not competitors. They are complements. Webb finds the needle in the haystack. Roman shows you what the entire haystack looks like. Together, they represent the most powerful combination of space-based observatories that astronomy has ever had available at the same time. There's a line that the project's senior scientist Julie McHenry used in the lead-up to Roman's completion that has stayed with astronomers who heard it. She said that within our lifetimes, a great mystery has arisen about the cosmos, why the expansion of the universe seems to be accelerating. She said there is something fundamental about space and time that we do not yet understand, and Roman was built to discover what it is. That sentence carries the full weight of what this mission means, not just the discovery of new planets or the cataloging of more galaxies, but the possibility of a genuine breakthrough in the deepest question physics has faced since Einstein rewrote our understanding of gravity. What is dark energy? What is the universe actually made of? Why does it behave the way it does at its largest scales? Roman will not answer all of those questions in a single observation or a single year. Science does not work that way, but it will generate the most powerful data set ever assembled for attacking those questions, and it will do so across 5 years of continuous observation, building a picture of the cosmos that is wider, deeper, and more detailed than anything humanity has ever attempted to construct. It will find planets that we did not know existed. It will map structures in the universe that we have only guessed at. It will measure the history of cosmic expansion with a precision that will force the competing theories of dark energy to either prove themselves or be discarded. And if there is a flaw in our current understanding of gravity or cosmology at the largest scales, if Einstein's equations need to be corrected or extended, Roman's data will be the place where that flaw first becomes undeniable. The telescope is ready, the rocket is chosen, the launch site is being prepared, and somewhere in the data that Roman will begin sending back to Earth in the months and years ahead, there are answers waiting that will change how every human being who hears them understands the universe they live in. 8 months early, under budget, and carrying the ambitions of every astronomer who ever looked up at the sky and asked why, the Roman Space Telescope is headed for the stars,